So here's MCAT. I think you've seen this formula from chemistry, right? This is the notion, is that if we're going to heat something, if we're going to make its temperature rise, okay, if we're going to make the thing's temperature rise, that is, we're going to change the kinetic energy of the molecules go faster, okay? The amount of heat you put in depends on how much stuff you have. If you have twice the stuff, it's going to take twice the amount of heat. It also depends on the temperature. If you want the temperature change to be twice as much, you've got to have twice the heat, right? And then the final thing is this specific heat, right? Okay, and it turns out that not all substances are as easy to heat up. Some are harder to heat up, like a kilogram of the substance, 1 degree Celsius, right? Some take a lot of heat to do that. Some take not very much heat to raise 1 kilogram 1 degree Celsius, right? The amount of heat needed is actually specific to the material. It's one of the physical properties of a material, like its density or its hardness or something like that, right? Okay. This Q that we're talking about is a change in kinetic energy, okay? Why? Well, because temperature is proportional to kinetic energy. If the temperature doesn't change, the kinetic energy of the particles in the substance doesn't change, right? And then finally, here are some specific heats, okay, of the substances. And the units are joules per kilogram degrees Celsius. This is how IB writes it. The rest of the world, by the way, writes it this way. Joules needed to raise 1 kilogram 1 degree Celsius. That's what it means, right? Okay. Well, if you have a kilogram of liquid water, it takes 4,186. There's that number again, right? That's just a calorie in joules, right? Or a kilocalorie, right? And ice, for some reason, when it's ice, it's easier to heat up. Go figure, right? Steam, boy, that's even a bargain, right? Okay. Aluminium, right, is 900. I'm just saying aluminium. The British say aluminium. We say aluminum. Okay. Iron is 450 joules, and there's more in your book. You can look those up. Yeah, there we go. All right. This is just, before we go on and do like an example problem or something like that, right? This is, I think this is interesting, right? This is the stuff in joules per kilogram degrees Celsius. This is the same exact thing, but it's not per kilogram, it's per mole. Now, what do you notice? Well, if you look at this column, we're all over the place, right? And you look over here, and they're all pretty much ballparkish, right? They're like, what do you say, 25 plus or minus 25 and a half, I don't know, plus or minus 1. Yeah, just about, right? There it is. They're all sort of centered around 25, except for, one of these things doesn't go together. And of course, the difference is that these are metallic bonds that we're talking about here. These are all metals, and carbon is network covalent or some weird thing, right? But anyway, I thought that was interesting, right? Is that aluminum probably has a lot, right? Does that have to do with the density? Probably does, yeah, because look how small lead is, right? Anyway, so mole per mole, it's all about the same. Okay, so let's, we got an example here, right? A, nickel S, cheap, wants to calculate what heat is needed to raise 1.5 liters of water by 5 degrees Celsius. So remember, a liter, if it's, distilled water, is 1 kilogram. So this is 1.5 kilograms. So Q is mc delta T, and then mass is going to be 1.5 kilograms, and then water, assuming it's liquid water, right, is 4186. And again, these weird way of writing the units there, that just means this, joules per kilogram degrees Celsius, right? Okay, and then 5 degrees Celsius, right? Okay. And then that just takes some calculating. 1.5 times 4186 times 5. That's a lot of heat. That's 31,395 joules. Right, I guess with sig figs. All right. So these aren't really not that hard. Just remember, we got different units. It's not grams. I'll go ahead and do some example problems, though. Look at that.